So in my previous lecture we started with first order logic, and we also looked into the key components of first order logic and the syntax and meaning of syntax and semantics under the umbrella of first order logic. Now let us move further in order to explore some more details of this FOL. One very common term which is used in first order logic is WFF, which is nothing but well formed formulas. So well formed formulas in first order logic are the expressions which are constructed obviously according to the syntax rules of FOL. If they are not going to be constructed according to the syntactic rules of FOL, they are not going to represent the true meaning. So these are the expressions which are constructed in accordance with syntactic rules of the FOL, and they also represent meaningful statements about the world or about the we can say domain of discourse. And these formulas serves as the building blocks for encoding knowledge and reasonings in AI systems. Now let us see what are these well formed formulas, what are the examples of these WFF well formed formulas, and what are the characteristics of these. So first characteristics, as I have already told you while explaining, is the syntax compliance. Well formed formulas must adhere to the syntax rules of the first order logic, and these syntax rules are going to define how terms, predicates, quantifiers and logical connectives can be combined to form valid expressions. So it is not about only the kind of syntax compliance. We also need to be careful about the symbolic representations. That means these well formed formulas consist of symbols representing terms, and these terms could be constants, variables and functions, and not only the terms but there can be predicates which are nothing but the relations. Then there are quantifiers which are for all and they exist, and then there are logical connectives. So these well formed formulas, they consist of terms, predicates, quantifiers and logical connectives, and they are to be structured according to the syntax rules of first order logic. So if in combination I can say both the characteristics. So well formed formulas consist of these terms and the structure should be kind of according to the syntax rules. Then there comes quantifiers. So quantifiers scope is to be maintained very clearly. Well formed formulas maintain clear quantifier scope, ensuring that these quantifiers binds the variable appropriately within the formula, and we are going to look into some examples of this quantifier scope. The scope of quantifiers affects the interpretation and meaning of the formula. So if you are going to so you have for all x and then there exists y, and if we are going to change or if we are going to reverse the position of the for all and there exists, this is going to kind of change the interpretation and meaning of the whole formula. So example is I am going to cover this example soon. Then we have important characteristics of well formed formula is complexity and nesting. That means these well formed formulas can range from simple atomic formulas to very complex nested structures involving multiple quantifiers, so many connectives, and in order to have an unambiguous interpretation, it is very necessary that the proper nesting and proper grouping of sub formulas is to be kind of done in a proper manner, so that a correct, a valid and an unambiguous interpretation of the whole well formed formulas can be interpreted. Now where are we going to use this WFFs, or what is the importance of these well formed formulas? So first of all, you must have understood by now that in order to represent the knowledge, these well formed formulas are going to serve as the formal language for knowledge representation about the world in AI system. Now that world can be can be confined to a particular domain in which that AI system is working, and these WFFs enable the encoding of facts, rules, constraints and relationships in a structured and precise manner. So, the first importance of well formed formulas is they are used in knowledge representation, and it is not about the knowledge representation. The second important point about well formed formulas is about the automated reasoning. These AI systems, or what AI agents and systems we are going to build, they are going to utilize well formed formulas for automated reasoning tasks such as deduction, inferences, logical decision making. Well formed formulas facilitate the application of formal logic principles to derive the new information from whatever existing knowledge your AI system is having. So, in this way they are going to help in kind of logical decision making and some automated reasoning as well. Then there comes the characteristics of semantic understanding. Understanding the syntax as well as the semantics of WFF is crucial for any AI system which is working for NLP or which is working with NLP. So, for NLP systems to interpret and extract meaning from the textual data, it is very important to understand the syntax and the semantics of WFF. Mapping natural language statements to logical representations involves recognizing and constructing well formed formulas, and that too it is not about just recognizing and constructing well formed formulas. Those well formed formulas should be kind of we can say correct according to the syntax rules obviously, and they must have kind of an unambiguous and clear accurate interpretation. Then in AI problem solving and planning, any AI planning and problem solving domain, these well formed formulas plays a key role in defining the initial state of kind of whatever a search method we are going to use. So, whatever the initial state of the world or whatever is the initial state of the problem, then what is going to be the goal state that is to be achieved. Then there are transition rules of the problem, and this all details we have seen in our minimax algorithms and the algorithms for problem solving and planning. So, I am sure that you understand all these terms: initial state, goal state and the transition rules. So, they enable the formulation of logical constraints and objectives for automated planning algorithm, in which the idea is to move from an initial state to a goal state with the help of or by following the valid transition rules of the problem. Now, when we say when I have started with this logic in AI, I have already told you that there are some advanced concepts which we are going to cover, and for that these prepositional logic or maybe this first order logic are going to be kind of basic building block or fundamental items. So, what are those advanced concepts are available? Let us try to understand them very briefly, and then definitely we will be devoting a few more lectures on these advanced concepts. So, the first advanced concept in first order logic is about unification. Unification involves finding the substitutions that make two expressions identical, and it is used in automated reasoning in order to match the pattern. So, for example, we have a family tree and I am asking, let us say, a father x comma y. So, wherever there is a father and the children kind of relationship is there, all those names or all those constants will be unified or x and y will be unified using the value of all those constants. So, this is what unification is, which is nothing but finding the substitutions that make the two expressions identical. Then there comes very important topic which definitely we are going to cover in very detail is resolution. Resolution is nothing but a rule of inference used in theorem proving to derive contradictions and in order to prove or disprove the statement. So, when we use AI for theorem proving, resolution is a very important kind of we can say checking or an important validation. Then we have logic programming also, as I have just given the example of father relationship. So, in logic programming it is all those languages which are like Prolog for AI applications, and these are used in NLP and expert system. So for those logic programming, these kind of advanced concepts, these first order logics are going to be used in the logic programming also. Apart from logic programming, there is a concept of model checking. So model checking is about verifying whether a system meets a specification used in hardware and software kind of verification, yes or no. So this model checking process verifies whether a system meets its intended specification, hardware and software both. Now till this point we understood propositional logic, and we also tried to understand first order logic, but there are some kind of fundamental differences between these propositional logic and first order logic. Let us quickly go through these differences. So when we talk about the propositional logic, we are representing an entire statement as true or false. So for example, the road is wet, or the example is it is raining. So that statement could be true completely, kind of that whole statement or that entire statement is true or false. Now first order logic is more expressive as it represents some relationships, properties and some generalization. For example, all cats are mammals. Propositional logic is not having any quantifiers, but when we talk about first order logic, it uses quantifiers which is for all and used for generalizations, and the existential quantifier which is used for kind of some specifications. Then we move on to the propositional logic. It is having some basic logical operations and or not, while the first order logic is able to reason out the statements in an advanced manner with the help of inference rules, with the help of all those advanced topics which we have just seen, like unification or maybe kind of resolution. So in order to talk about unification and resolution, we need to have first order logic. By just merely having the propositional logic, it is quite impossible to work in these advanced reasoning mechanisms. Then in propositional logic, if we talk about, there can be some simple tasks, or it is used to achieve some simple tasks like decision making and circuit designing. While when we talk about first order logic applications or the first order tasks in which it can be used, so they can be kind of very complex, which say knowledge representation, then reasoning, language processing and so on and so forth. So we have seen that yes, definitely this first order logic is having an upper edge on this propositional logic, because it is having some more, it is actually more expressive, and it is having sophisticated facilities. But with these things there comes different challenges also. So when we talk about the challenges of first order logic, so first of all, it is computationally complex. So reasoning with large knowledge bases or large storage of knowledge data, it can be very resource intensive, which makes it difficult to kind of scale up. Then there comes the challenge of expressiveness versus decidability. So while FOL, which is first order logic, is highly expressive, it is undecidable, means that there are these statements that cannot be resolved algorithmically. Then when we come to the topic of handling uncertainty, just like the propositional logic, FOL also does not handle uncertainty well in order to manage the real world ambiguities, and extensions like fuzzy logic or probabilistic logics are used. So alone, if we talk about FOL, it is not able to kind of handle the uncertainty in a proper manner. Here also, when we are studying first order logic or first order predicate logic, predicate logic is also based upon the predicates, and these predicates consist of two key elements. One is the predicate symbol and another one is the arguments. Also these predicates are enhanced with quantifiers in order to specify the scope of variables involved. So, in order to understand the predicate completely, we need to look into the scope of quantifiers as well. So, first of all, let us see how these predicates are made or what are the examples of predicate. So, when we say predicate, the predicate symbol defines the property or the relationship being described. So, for example, a predicate symbol is let us say is hungry, and within the bracket I am writing X. So, that is actually a representation that whether a person X or whether X is hungry. Then when I am saying married X comma Y within the bracket, that denotes that person X is married to person Y, and actually these are the examples of predicates, or these kinds of predicates we are going to use. So, when we say predicate symbol within the predicate, these predicates are named based on the relationships or the property they represent. So, for example, married or for example is hungry. This is actually the relationship or the property which is being represented. The symbol is followed by the arguments enclosed in the parenthesis. So, for example, is hungry X. So, the predicate symbol is hungry, X is the argument. When I am saying married X comma Y, so that means this predicate symbol which is married is having two arguments which are enclosed in the parenthesis, and these are nothing but X and Y. Now, arguments refers to the specific objects that the predicate is on which the predicate is applied. So, for example, is hungry is applied on X and married is applied on X comma Y. So, with these arguments we have one concept which is known as arity. So, arity of a predicate refers to the number of argument it takes. So, for example, I am talking about is hungry X, it is a predicate with one argument. So, that means arity of this is 1, and married X comma Y, a predicate with two arguments. So, arity is 2, and for example, I am writing any other predicate with the name let us say X. So, where the capital X is the name of the predicate and A, B, C are the arguments. So, a predicate with 3 arguments which is defined with arity equals to 3. So, arity is nothing but the number of predicates. So, for example, this could be A, B, C plus A plus B plus C is equals to 0 or something kind of whatever, it could be different from that. Now, apart from these predicates, we talked a lot about quantifiers which allows us to specify the scope of variables, and we have seen that there are two quantifiers. One is the universal quantifier for all. This means that the given condition holds for all objects in the domain. So, for example, for all X is human X implies is mortal X, that means all humans are mortal. So, X is a man, then X is mortal. And if we are going to put the negation in front of universal quantifier, or the negation of the universal quantifier means that at least there is one exception. So, negation for all X is human X implies is mortal X says that, or it is interpreted as that at least one human is there which is not mortal. So, we have seen universal quantifier along with its negation. Moving forward to existential quantifier. So, existential quantifier, that means there exists at least one object that satisfies the given condition. So, for example, there exists X is hungry within the bracket as the argument X is being passed. So, this statement means that at least one person is hungry, and if we are going to apply negation in front of this existential quantifier, or the negation of the existential quantifier means that no such object exists. So, for example, negation there exists x is hungry x will interpret it as no one is hungry. So, putting the negation in front of or negating the existential quantifier is different, and negating the universal quantifier is different. So, when we are negating the existential quantifier, that means no such object exists, and when we are negating that universal quantifier, that means that at least one exception is there. So, this is a point to be kind of kept into the mind. Then if we look into some examples of predicates, for example, we have seen is hungry x, or if we are going to pass an constant in place of x. So, for example, is hungry John, which means that the predicate represents the state of whether John is hungry. It is taking one argument, which is John, so arity is 1, and it will return true if John is hungry, otherwise it will return false. So, that is kind of very well understood, or kind of self explained kind of thing. When we say the applications of these predicates in AI, in all the NLP based chatbots, predicate like this could help infer the user's intent. For example, if a chatbot detects that user is hungry, it could suggest nearby restaurants or something of that sort. Then we have one predicate which is known as equality predicate example. So, is hungry x was kind of a very simple predicate. Equality predicate says E x comma y is equivalent to x comma x is equals to y. The simple meaning is predicate denotes that x is equals to y, and it returns true if the two objects are identical. Now, if we look into the applications that where this equality predicate or something of this sort can be used, in all AI based reasoning systems, these reasoning systems use equality predicates to match objects. So, for example, in a robot warehouse, a robot may use this predicate to determine if an object picked matches the one which is requested. That means equal package 1 comma requested item. So, if package 1 which the robot has picked is equals to the requested item, so means you can go ahead, otherwise you need to abort the action. Then apart from the simple and equality predicates, another example of predicate is a mathematical predicate. So, mathematical predicate, as I have given you the example in arity 3, there is a predicate named as x, and within the bracket it is having a comma b comma c, and the predicate says a plus b plus c is equals to 0. This predicate checks whether the sum of a, b and c equals to 0. It will return the true if the equation holds, otherwise it will return the false thing. Where these kinds of predicates can be used in AI. So, in all optimization problems, AI models might use the mathematical predicates to check if constraints are satisfied. So, for example, in scheduling systems, such predicates can validate if certain conditions are met. So, for example, shift A plus shift B plus total time will check that whether the shift hours are balanced or not. So, then we have relationship predicates. So, relationship predicates we have already seen an example married, or we can just write m x comma y, which says x is married to y, meaning this predicate expresses a relationship between two objects indicating that x is married to y. And what is the application in AI, or where these are going to be used is simple, your family tree AI system, as I have already mentioned. Relationship predicates are used to infer the relationships among family members. So, for instance, married or M John comma Mary is true. That means the system will infer that John is Mary's spouse. So, this is how this kind of relationship predicate predicates are going to be used. Now, when we say universal quantification, we have seen one example. For all x is human, x implies is mortal x. This statement reads as, for all x, if x is human, then x is mortal. This essentially means it applies to every object in the domain of humans. If an object is found to be human, it must also be mortal for the statement to hold true. Now, where it is used in AI, in knowledge based systems, such rules are used to infer properties about objects. So, for example, in a medical diagnosis system, all viruses can spread infections can be written as, for all x is virus x can spread infection x, and this will help the system to reason about the diseases. Then we also have this existential quantifier, for all x is hungry x, and we have also seen the kind of meaning. It indicates that at least one object in the domain satisfies the condition of being hungry. Now, where it is actually going to be used in AI, maybe in kind of robot planning. A robot could use existential quantifiers to plan actions. For example, there exists a task that requires charging. So, this can be written as, there exists task requires x comma charging, might guide the robot to prioritize the charging task. So, we have seen that how these existential quantifiers, universal quantifiers and the simple predicates, relationship predicates are going to be used in various applications. So, what I am able to understood is you must have got the meaning of these predicates, how these predicates are written, simple predicate, then equal predicate, relationship predicates, and how these quantifiers are going to be used. Definitely quantifiers, or we can say the order of quantifiers matters, and there is lot going to be covered about this order of quantifiers and other nuances of first order logic, but that will be covered in our next lecture. Here is a list of references which is being used for the preparation of this one. I hope you have enjoyed this one. Till then, I will see you in the next lecture. Till then, take care. Goodbye.